Sure. Okay, guys, can you see the screen?
Yes, sir.
Okay. Right there. So do you remember what we discussed in the last class? Hmm? Hello. Anyone remembers what we discussed?
Hello. Sir, we discussed how to block DC from the signal.
And how do we do that?
Sir, we introduce a common emitter with emitter resistance, which is a PNP transistor,
Mhm.
cascade with a common collector NPN transistor.
And what is called that circuit? What do you call that?
So voltage level shifter, DC voltage level shifter.
Right. So we introduced the DC voltage level shifter. The common collector is just an output stage. The common collector that we had is the output stage.
Sir.
So we have gone through the different stages for this multi-stage differential amplifier. It's applicable for any amplifier, not just differential amplifier, the normal conventional amplifier. So first we have the input stage. So the purpose of the input stage to provide high input resistance, right? So that Ri should be high. And then you have the intermediate, you have the gain stage. Gain stage provides high voltage gain. You also have current gain, but the main purpose of the gain stage is to provide high voltage gain. And then you have the DC voltage level shifter. And then you have the output stage. Then you have the V naught. The output stage there, this has several functions, and for different purposes we use output stage. One is to minimize loss of gain. When you connect a load resistance, as you've seen in the last last lecture, that load resistance, if it is low, then your gain will be low. So by inserting this output stage, you can minimize that loss of gain and provide, when necessary, provide high load current. So before the input stage, the different stages, the main function is to provide high voltage gain, keeping the current low as possible. Then at the output stage, provide the current that is necessary for the load. Now, because the high current means high loss, right? I square loss increases with the increase in current. So at the input and other gain stages, it is the main aim is to keep the current low so that we can keep the losses low, right? And only at the output stage boost the current and provide high current gains. So that is needed by the load, because load will need both, right? They will need the voltage and the power, high power. High power means high current, right? VI is there. So both high voltage and high current. And that is both we can achieve using the common collector, as we have shown in the last class. So something like this. RL. Now, in the integrated circuit, we bias the transistor by using the current source. If you are designing discrete amplifier circuit, then you would use a number of resistors here, R1, R2, RE, RC. But here, we do not use those resistors because resistors consume a lot of power. And then we use current source to supply the current, bias current. So you have, let's say, I, and that is your input. So that is our output stage, common collector, which is usually common collector. So then the resistance, the input resistance of this one, this is the effective load resistance, right? Because that is what is connected to the amplifier, and amplifier will see this is the effective load resistance, which is beta plus 1 times RL, right? So now load resistance goes up so that gain will not be affected that much. And okay, so that we discussed in the last class. And also we said that at different stages, when you design the amplifier circuit, you have to ensure that all the transistors are properly biased. And biasing means the both, right? Or the current and the voltage, both the collector current and collector voltage. They are, high enough to support your signal voltage and current, which is also known as the operating point, right? So that you need to ensure, and we have discussed in detail how to check for the bias voltages if they can support your signal voltages. For a whole range of signal voltage, you have to see that this of course will remain forward biased. In addition to that in the collector base voltage, right, remains reverse biased. So for all range of your whole range of your signal voltage, this remains reverse biased. That is how you ensure that your transistor is operating in active mode. Now, today the main focus first is on the current, right? we discuss in detail about the voltage, but not that much on current. So how to ensure that your bias current is, high enough to support your signal current. You can take very high value of current. Let's say that you take I. This I is the bias current 1 milliampere. Right? So that is 1 milli is very small. Let's say you take 1 ampere. So you take 1 ampere current. This is large current, and that will obviously satisfy your requirement. This is your, let's say, load current I naught, signal current. The condition is that your bias current should be greater than or at least equal to I naught, right? So if a bias current is greater or at least equal to I naught, then it will be able to support this load current for all range of its values. And let's say that your I naught you require is 100 milliampere, right? And you take a bias current of 1 ampere. Obviously, that will satisfy your whole requirement. For all range of values from 0 to 100 milliampere. But that will also increase the power loss because you are taking a too high value of current, and then power loss also goes up. So that is not be an optimum value. So optimum value should be somewhere close to this. If it is 100 milliampere, probably you can take, let's say, 110 milliampere, slightly larger than this. So if I show it in the graph, it will be something like this. Let's say this time axis, and this is our current, right? Let's say ampere or milliampere, whatever. So if this is our, let's say, our bias current, this is our bias current, and our signal current is something like this, right? I naught. Right? So signal current superimposed on the bias current that will flow from here, right? So here we'll have I plus I naught. So here you have both the DC bias current and the load current, and load current is fluctuating with time. So that is what you have here, the total current, right? Basically, just if you take this the signal current, it will be like this, right? And this is the total current here, and this will be your signal current, I naught. So this is more appropriate if you write I plus I naught. So that will be total current. This is your DC bias current. This is your signal current. So that is working fine because the current is flowing in this direction. That is how it should flow. Now, if your signal, if your load demands larger current, so it will go like this, right? The total current will vary like this. If it demands even higher current, so it will go like this, right? If I naught increases, it will go like this. For larger load current, it will go like this, right? Now, what happens that, let's say your I naught, this maximum value of I naught is greater than I, right? The maximum value of I is greater than I. The maximum value of load current greater than I. So you have the current flowing like this. It will go below this. Okay. So here you have the zero value, and here we have the negative, right? So let's say -1, -2, something. So current will go negative, and total current here go negative. Negative means that it is has to flow in the opposite direction. Right? Negative means it has to flow in the opposite direction. But we know that in the transistor, the current cannot flow in this direction. So this arrow indicates that current will flow in this direction. It has to flow in this direction. And whenever it tries to flow in this direction, it will turn off, right? It will turn off. Transistor will go into cutoff, and I will be zero at that time. The I naught will be zero. It cannot go negative, right? So it will become zero at that point. So so that's what it will happen. So you cannot, the Bascan will not be able to supply or will not be able to support this current I naught, right? So when the I naught is larger than I, so I has to be greater or at least equal to I naught. Is that clear, guys?
Yes, sir.
Okay, now let's we consider some specific situation. Now let's say V naught, the maximum value of V naught is 5 volt. Then RL, let's say, is 1 kilo, right? Then I naught max is your V naught max by your RL, right? And V naught max is 5 volt, and RL we have 1K. So that gives us I naught max is 5 milliampere. So in that case, if we choose I 6 milliampere, right? So I think that will be good enough for the bias current. So when I naught is 6 milliampere, so the current that will be flowing here, that is we call IB, right? And how much will be IB? IB will be,
Sir,
this
I
is
equal to IE by or 6 by 1 plus beta.
right, IE by beta, right?
Yes.
Beta plus 1. Okay. So if I is our, this is 5 milliampere, so 5 milliampere divided by beta, beta, let's say 101, right? So approximately this will be 0.05 milliampere, right? So that is not that high, that is okay. Imagine that this is connected to the output of the amplifier, right? And if you are using that multi-stage differential amplifier, what we have here, we have basically that the voltage level shifter. This is we have RE. then we have RC, right? And here we have this current IE. So now this one, let's call it IE3. Q3 was there. This was Q5, right? So let's say this is our IE3. Now, how much we assumed IE3 to be? In our previous analysis, we assumed IE3 to be 1 milliampere. Remember? That is how we designed this circuit. So you can assume other values, then you have to reduce IE. If you want to design IE3 for some other values, in that case, it was 2.3 we took RE. That gave us IE about 1 milli. If you reduce this resistance to half its value, then you will get 2 milliampere. So that will depend on this. You can change the value of IE, this current, by changing the value of resistance. Now the current that will go here, IB, you need about 0.05 milliampere. And this current, this IE has to supply this current, right? For the voltage drop here, we need 0.7 volt, right? We need 15.7 volt drop here. For this drop to occur, so we assume the current of 1 milliampere flowing here. Now, when this one is connected to this, we see that this IE, it has to supply not only this current, but also the base current of this one. So 0.05 milliampere will go from this 1 milliampere of current, right? So basically, you will get not exactly the current here. This, let's say this is IC3. So that will not be exactly 1 milliampere, but it will be 1 minus 0.05, about 0.95 milliampere, right? So you need some kind of adjustment, little bit of adjustment, slightly higher values of RC, right, to adjust the voltage drop. Is that part clear?
Yes, sir. Sir, how IE is 5 milliampere? Sir, IE, the previous IE, how it is 5 milliampere?
5 milliampere, this is this one here, no?
Yes, sir.
That's IE. Because you need to supply a current. Load current, maximum value of load current is 5 milliampere. And then
Yes.
I, oh, it has to be 6, no? Sorry, you wanted to say it's 6 too, right?
Yes, sir.
No, yeah, that's a mistake. So I should be 6, right? So then that means IB will be 0.06, and this is 6, so this will be 0.94. Okay, so a little bit decrease in the current, this bias current, and so you'll need to increase the value of resistance by the same margin, right? So that voltage drop here, you get 15.7 volt. Is that part clear?
Yes, sir.
So you need IC3 and RC. This was let's say 3. RC3 to be 15.7. What happened here? Oh, it is doing like this. This is getting complicated. Okay, 15.7 volt, right? Now, so you have to choose RC3 accordingly. RC3 should be now 15.7 divided by IC3 is 0.94, right? Volt and milliampere. So it will not be exactly 15.7 as we have taken RC3 in the last, we found, assuming that this is 1 milli, but it's little less than 1 milli, and you need to then adjust this. Or you can increase the value of IC, so it is 1 milli, and then it will be 15.7K, whatever. So there has to be some adjustment here. And that is not a big deal. You can easily do that. Now imagine the other situation. Now here we have right? Before we had 1K, now RL is only 10 ohm. And how much RL is there for your project? What is the value of RL? Have you seen that? I guess not.
Yes, sir.
How much? No? Okay. So just focus on this. If RL is 10, what happens? You have VO max divided by RL, right? VO max remains 5, same as before, but RL now is 10 ohm. So that means current you need 0.5 ampere, right? That is almost 500 milliampere. Right? So before current was only 5 milliampere, and now you need current 500 milliampere. So the lower is your load resistance, the higher will be the current, right? And the higher is this current, the higher you will need the current for I, the bias current. So bias current has to be greater than or at least equal to your I naught max, as from our previous discussion. So what we can choose the value for I in this case, since it is 500 milliampere. So let's say we choose a value of 550 milliampere, right? 10% greater. So then our minimum value for I will be this, right? At least we'll have this much of current flowing. So that current will determine then IB, right? How much IB will flow here. So in this case, IB is your 550 divided by beta plus 1, which is 101. And assuming approximately if we take 100, then it will be 5.5 milliampere. Is that correct?
Yes, sir.
So now what is the problem? See the problem here?
So the base current is much higher.
Right. Now you see that this current here, IB is 5.5, and here you have current of only 1 ampere, 1 milliampere, while this in the common collector, the output stage needs a 5.5, much higher than what you have here. So this will not be able to provide that high base current, right? When it will demand this high base current, it will go off, right? This stage will go off. It will pull all the current and then shutting it down, right? So the circuit will not work, right? Your circuit will not work. So what is the solution here? Now, you can design the circuit to supply this, no, it needs to supply 5.5 and 1 milliampere here. So you can design this circuit so that IE is 6.5, right? You can do that, but that is not a good design. That will not be a good design because this is now it has so much high current, right? The power losses will be high, right? And for a long time operation, this will increase the temperature, deteriorate the performance, right? So there are many other issues, right, that you will have with this high current. So what is the solution?
So can we add a voltage buffer here?
Yeah, we can use another voltage buffer. That is exactly what you can do. But instead of voltage buffer, we use a Darlington pair, which is actually basically the same thing. But Darlington pair, which is considered as one single device, which comes in one single package. Right? So let's say this is our IB1 and that is our IB2. Now, when we have this, now see that IE, the same IE, we have to take, will be equal to I1, this is IE, and that is equal to IB2, right? This kind IB2, right? And IB2 will be your I2 divided by beta plus 1. Right? So which was in our case, this is 5.5 milliampere. And now you have the current here flowing this IE and or I1 and IB1 will be this IE divided by beta plus 1, okay? Which is now your 5.5 divided by 101, and that will be approximately 0.055 million. So the current here now, again, around the same value what we had before with 1 kilo ohm resistance. The current, maximum current was 5 milliampere. We took 6, okay, 6. The IB was about 0.06, maximum current was 5 here. And now here, when we need the maximum current of 500 milliampere, and we designed for the bus current of 550, so the IB needed was 5.5. Now, using the what we call the Darlington pair, Now that reduces to again 0.055, around the same value what we had for, with for the previous case. Is that clear? Any question, guys?
No, sir. So now we have uh, left our dependency on the RL, right?
Right. So because the input resistance for this Darlington pair is very high, right? So the resistance that you see here, right? So that is Ri, the output stage, right? So that is very high. So that will be almost independent of this RL. And this is our Darlington pair you'll be using, right? So Darlington pair, this will take care of this current when the output current is very high. It will supply this high load current to the load, and at also same time it will reduce the pressure on this previous stage to supply, right, the high current. So the current needed is very small, and this stage now will be easily provide that or support that current. And also the Darlington pair has a very high current gain, right? So, mostly this has to be a power transistor. Right? So this you have to, notice these differences between the requirement of the different circuit components at the output stage and the stages that you have before. Because the current here is only milliampere, and you can use regular transistors, but at the output stage current in the range of ampere, right, or hundreds of milliampere. So regular transistor will not work, right? They will not be able to sustain that high current. They will melt. So you need to use power transistor that can handle that high current. So there are transistors, power transistors of different current and voltage ratings. So you have to take that is suitable for your application. Any question, guys?
No, sir. Sir, by power transistor, we are defining that it can supply a high current, right?
Yeah, it can withstand high current. When the load will demand high current, it can sustain, support that high current without, without collapsing, without melting down.
Okay. Sir, it is built with the normal regular BJTs, right? Or power, I mean, the power electronics or something like this.
Power electronics is a different thing. Power electronics means the electronics that is used to manipulate or control the power, right?
Yes, sir.
The electronic device and circuitry that control the flow of power. So the part of electronics that deals with that is called the power electronics, right? So we are not dealing with power electronics, but the electronics that can support high power, withstand high power. So those are also called power transistor, right? So they are designed and built in a different way, right? They'll be bigger in size, of course, right? This is normal. I mean, our knowledge that when you need to have high current flow, right, through a conductor, the conductor will get this thicker, right?
Yes, sir.
The dia will increase, right? The higher is the amount of current, the bigger will be the cross-sectional area of the conductor, right?
Yes, sir.
So same thing applies here. The current has to flow through the device, so the device has to get bigger, right, to accommodate that current. So the power transistor that has to deal with the large current are bigger in size. Right?
Yes,
That
sir.
is one aspect. The other aspect is that since large current is flowing, so lots of heat is generated, right? So to dissipate that heat, they also comes with built-in, radiator, heat radiator, the metal
Heat
coating
sinks.
things here, so that are designed to dissipate the heat. So they come with this metal casing. The normal fans that you use in the lab, they have the plastic casing, right?
Yes, sir.
But they will have those metal casing and big in size.
So metal casing like the voltage regulators.
Voltage regulator. No,
Yes.
not all voltage regulators, they have metal casing.
Uh,
It
some
depends
of
on
them.
the
Yes, sir.
size, the requirement of the current and voltage. If they have to deal with the high current, high voltage, high current, then they come with metal casing. Otherwise, they also come with, for low current, milliampere range current, they come with plastic casing.
Yes, sir.
Okay, so that is all about the differential amplifier. Our next topic will be the current sources and current mirrors. So far we are showing these current sources using this right symbol. This is a symbol of the current source, right? That are used to design the that are used to bias the amplifiers in integrated circuit. In discrete amplifier, we use the network of resistors to bias the transistor amplifier, but in integrated circuit, the current sources are used instead of those network of resistors. So our next topic is how we design, construct this current sources circuit. So let's take that example of this, what we have shown just now. The output stays, we have this this is our voltage coming to the output stage, and then we have this load, and then we have this current source, that is I, right? Here we'll have the voltage minus VEE. So our focus here is this part, right? How to design this current source circuit that can supply the current that we need, right? So there are different ways to do that. Why it is calling this? The circuit here, that this one will work as a current source, and this is connected, let's say like here, this is our current source, the whole circuit. uh, so this one whole is our, right, this transistor with this resistance in the base RB is your current source, and that is supplying this current I. So the current that is flowing here, this is our current I, right? And that will connect it or supplying the current to this a transistor, which is our common collector amplifier, right, the output stage. So that is connected to the amplifier supplying the bias current I. Now, how do we fix this current I? Let's say this voltage is VBE, right? Now, if you apply the KVL here, so you have voltage drop. Okay, let me change this one again. So we have voltage drop IBRB, and then we have VBE plus VBE, and that will be equal to the supply voltage, which is VEE. So that is the equation that we will get if you write the KVL around this loop. And solving this, we get IB is minus VBE, and that divided by RB. So that will be value of IB, and then I is basically nothing but IC. So I is equal to beta IB, right? And that we can write as, okay, we can write it here, VEE minus VBE divided by RB by beta. So that will be our current I. So if we know that you can fix VE, and we can adjust RB, right, for different values of current I. So by changing the value of this resistance, we can also adjust this current, right? So that is how we can design a current source, right, for the amplifier. Any question?
No, sir.
Okay. There's another way of doing this. Instead of putting the resistor in the base, we can also put it in the emitter, and we can show it like this. And this goes to ground. Minus VEE. So current here is I. Now this is voltage VB. Okay. So that is another way of constructing this current source. And here, if you write the KVL around this loop, so what you get VBE plus IERE, and that is equal to VEE, and we get IE will be VEE minus VBE divided by RE. And I is IC, which is alpha IE. Right? Alpha is close to 1, so you can just approximate, you can write this approximately equal to RE. So by adjusting the value of this resistance RE here, right, you can adjust this bias current. So these are the two ways, and there we can also have current sources using the, this is we are using NPN transistor. We can also have current sources using PNP transistor. So that we can show like this if you are using PNP transistor. So in this case, IB flows in this direction. Now we have VEB drop here, the emitter to base, and the current, this is the collector side, and the current, actual current just flows here. Now the difference between the NPN and the PNP transistor current source is that in this case NPN transistor, the like here in the example, the current source is connected below the actual amplifier circuit. So this is pulling the current through the amplifier. Right? Current source is placed below the amplifier and is pulling the current through the amplifier circuit. And in case of PNP transistor, if you are using the current source using the, it will be placed above the amplifier circuit. So amplifier circuit will be below this, right? And this current source circuit will push the current. It will push the current into the amplifier. right? This is pulling through the amplifier, and this PNP will push into the amplifier. So this is the basic difference. And in this case, the IB, so IB we can write as will be VEE, the supply voltage minus the drop VBE, sorry, is VEB. VEB divided by RE. And using the same formula, I will be beta IB. So, and that will be VEE minus VEB divided by, we will have RB divided by beta. So exactly same expression. There's all the parameters are same, but the direction of the current will flow, it changes. Any question, guys?
Sir, what
Yeah,
does pooling means? Pooling.
pulling. Yeah, pulling. No, you pull the rope. Pulling the rope down. Pull.
Yes, sir. But is it
Yeah.
is it pressurizing? Is it pressurizing the amplifier? The current source, is it pressurizing the amplifier to pull the current?
I don't know what does the pressurizing will actually mean. I mean, so you have to supply the current, no? And that supply actually is placed below, right? That controller, how much the current it will allow to flow through the amplifier, right? So that is placed below. So this will generate this current, and then this current has to uh, pass through, right, the amplifier that is placed above the current source, right? So this current source here that we have here, right, for the
Yes, sir.
amplifier, this is here, and that is generating this current. But if we didn't have this, if we didn't have this amplifier here, if we just supply connected here, then it will get the current from the supply directly, right? Now you have this transistor placed right before between the supply and the current source, right?
Yes, sir.
So then it has to pull through the transistor, right? So that was it is meant. I mean, it's
Okay.
just the way the current sources work, right? To indicate the difference. So it is going through, right?
Okay, sir.
It has to pull the current from the through the transistor, right? It is not directly coming. So, something like that. In this case, this is pushing, right? Something you push down, right? Placed below, right? So you are pushing it
Yes,
down.
got it.
Yeah.
Sir, by pressurizing, I meant for this current source, it's pulling current through the amplifier. Will it heat up?
Yeah, for whether pulling or pushing, there is the effect will be same. Current will flow through the transistor and it will have some losses, right? And that will generate some heat. For it will be same, and the effect will be same for both pull and push, right?
Yes, sir. Got it.
And same as we said for the NPN transistor, there are two ways to put the resistor. We can put it either in the base side or we can put it in the emitter side. Same we can also do for the PNP transistor. Instead of the base, we can also place it in the emitter, and that we can show like this. Oh my. So here the resistor is placed in the base, sorry, the emitter, and then current I we can express as VEE minus VEB, right, divided by RE. Right? And I will be almost equal to IE, so that is we can just I is almost equal to right, IE. So by adjusting the resistance RE, you can adjust the current, right? Is that clear, guys?
Yes, sir.
Yes, sir.
Okay, that's great. So these current sources we can use to bias the differential amplifier circuit, as we have shown in our the discussions on the differential amplifiers. So that is how we have shown so far the our differential amplifier, two inputs, right? V1, V2, and then we have the supply VCC, DC supply voltage, and the current source, right? So now we know how to construct the current source circuit. So we can replace this one with the current source circuit. So did you get the idea?
Yes, sir.
Yeah. So now there's another current source circuit that is very popular and that's mostly widely used. That is called diode connected transistor. It's connected in a way that looks is like kind of a diode. So the base is connected to the collector, right? So base collector junction is basically shorted, and you have this is forward bias voltage base emitter, and the voltage here is the collector voltage VC. Now, whatever voltage you apply here, the same voltage appears at the base, and that forward bias the base emitter junction, right? So basically, it's kind of diode, right? You're applying this forward bias voltage and you're working like a diode. Though it's not a diode internally, but from the outside it appears that it's like a diode. So that's called diode connected transistor. Now the current that will flow here, I, let's call it I. So what will be I? I will be VCC minus VC divided by RC. Now VC is nothing but the base emitter voltage VBE. So this we can write as VCC minus VBE divided by RC. Right? So by fixing this RC, you can fix this current I. Right? It's a constant current I will flow. Now the circuit just like this is not very useful because you have supply voltage here and this side is grounded. But this we can extend by connecting another transistor here. If you connect like this, so let's say this is our Q1 and this is our Q2. Right? Now you see that these two transistors Q1 and Q2, their bases are tied together. So what happens that when, in this case, since their bases are tied together, so they will have the same base to emitter voltage. They have a common base to emitter voltage. Let's say current flowing here is I1, and then here the current, the collector current IC1. And then current here is I2, right? And which will be same as the collector current IC2. Right? Now for the transistor, the collector current, the equation of the collector current with the base voltage is given as like this. IC is IS e to the power VBE, right? VD. So this equation has a lot of similarity with the diode equation. The diode current is equal to the IS times e to the power VD, the diode forward bias voltage divided by VD. In this case, the base emitter voltage. So base emitter voltage, it determines the collector current, right? And it's the exponential relation. Right? So by controlling the base emitter voltage, forward bias voltage, you can control the collector current. And that is the basic principle that is used in amplification. By small change in the base emitter voltage, you get a large change in the collector current. Right? So that is how the amplification, we get the amplification. And that same principle is used in this case to design the current source circuit. Right? Because transistor is like a current source, the collector current remains constant as long as base emitter voltage remains constant. and there's the exponential relation. So the transistor works like a voltage-dependent current source. Right? The current IC remains constant, and it depends on the input voltage. Right? So by controlling this voltage, you can control the current. So it's like a voltage-dependent current source. And IS is, it's called the saturation current. The what we have for the diode, we call the reverse saturation current, right? And the saturation current that depends on the size of the transistor, as I mentioned in the in the discussion in the couple of minutes back. We are discussing about the power transistor. They are bigger in size, so that they can accommodate and higher current, right? So the IS depends on the size of the transistor, the cross-sectional area of the transistor. The bigger this is, is the transistor, the higher will be the IS, the saturation current. So IS we write basically is proportional to the AE. AE is called the emitter cross-sectional area. So that is the emitter cross-sectional area. So for larger transistor, you have a higher IS and higher collector current for the same base to emitter voltage. And that is how we can have larger current, right, for the transistor. So the higher current you need, the bigger will be the size of the transistor. So now we have the same base to emitter voltage. So we can write that I1 or IC1 will be IS1 e to the power VBE by VT, and IC2 will be IS2 e to the power VBE by VT. And if you take the ratio IC1 by IC2, you will get this is part is same exponential, but you just get IS1 by IS2. Okay? And since the IS is proportional to the cross-sectional area, then it will be IE1, AE1 divided by AE2. Okay? So the current that will flow in the two transistors will be just proportional to their cross-sectional area. And if the two transistors are same, they have the same cross-sectional area, AE and AE. If they have the same cross-sectional area, then IC2 will be same as IC1. Is that clear, guys?
Yes, sir.
Yeah, IC2 will be same as IC1. And so this current is reproduced, right? The current that is flowing in Q1 is reproduced in Q2. And if we ignore the base current IB is usually much smaller than IC. If you just assume that this is 0, so we can say that I1 is almost equal to IC1, right? And IC1 is I2. I2 is same as IC2, and which is IC2 is IC1, IC1 is I1, right? So I2 is same as I1. Right? So current that we have established, right, in Q1, right, by choosing appropriate values of RC, this current we have reproduced, right, in the second transistor Q2. Right? And this circuit is therefore called the current mirror. Right? Current mirror. Current produced in Q1 is reproduced in current Q2, and this circuit is called the current mirror. Guys, any question?
Sir, the first amplifier or the transistor, sir, which operational region is it in?
Sorry.
So which operational region? I mean, it's active, saturation, or cutoff?
Obviously, it is not in cutoff, then current will not flow.
Yes, sir. So
And saturation, of course, not saturation. Then collector base junction has to be forward biased, right? But here, collector base junction is not forward biased. So I presume this will be in active mode only.
okay, sir.
But it's not working as an amplifier. We're not using this as an amplifier, right? So we don't need to worry about these modes. But this is in cutoff, sorry, in active mode. This collector base junction is not forward biased. Right? For forward biased, you need certain forward bias voltage, but you had it's just shorted, right? So voltage in the junction voltage is 0. So it is not forward biased. It is still, you can consider it to be reverse biased. So main beauty here is we can easily adjust this current here by setting the value. Let's say this is AE1 and this is AE2, right? And if the cross-sectional area, this AE2, if cross-sectional AE2 is 2 times of this one, if this is 2 times, then current here will be IC2 will be also twice the IC1, right? If the cross-section area is twice the cross-section area of Q1, then collector current here will be twice the collector current, and I2 to IC2, and that will be twice I1, right? So we can easily adjust the current, right, that we want to reproduce. We can generate a small current, but we can reproduce a much higher current, right, depending on our requirement, right, by choosing the appropriate size for this transistor. Any question, guys? Is that clear?
Yes, sir. Sir, someone in the chat box has some questions.
I cannot see chat box when I am presenting. What is the question?
Sir, he hasn't done yet. He is asking permission to ask questions.
Yeah, I can ask anytime question you are asking now.
He don't have any mic.
Oh, I have to leave this. Give me a minute. Let me finish this. I'll answer this question. So this is one, the beauty of this one, that we can have any amount of current, right, according to our requirement in our Q2. The other beauty is that this we can reproduce in a number of stages. So this is one transistor. We can have another transistor. Q3. And let's say this has a different requirement of current. So we have another different size, and that will produce another current I3, right? They have the same base 2 emitter voltage, but with different sizes, or the transistor sizes, right? So you generate the different amount of current in the different transistors. Like if you think about the multi-stage, our differential amplifier that we have discussed, that has the input stage, gain stage, the output stage, and all those stages will need different amount of current. So what we can do, instead of using what I have said, this one here, which is just one single unit, right, and cannot be extended, but we can use this current mirror circuit, right, to generate a current first, and then reproduce the required amount of current by choosing the appropriate area of uh, the emitter cross section, and supply to the different stages, right? As you know, the first stage we need small current, right? So the area will be small, and the second stage, gain stage, need a higher current. Then we need a higher cross-sectional area. The output stage will need even higher current, much higher current. So that will be even, you know, a bigger cross-sectional area. Is that clear, guys? The basic concept.
Yes, sir.
Yeah, and that you need to apply in your design. You know, the multi-differential amplifier, how to design the different current sources. So when are our quizzes due? There are no quizzes. Has the final date been announced? No, I think they have some final date in centrally. Probably they have assigned some date for the final exam. I am not sure. I have to look it up. Are we going to have final assignment? So this is your final assignment. The project is your final assignment. Any more question, guys?
No, sir.
So we'll have one or two, you know, the extra classes or makeup classes. I think we missed one or two classes, and we're a little bit behind our syllabus. So we'll find out when we can have those classes. Oh, so he could not hear my answer. Okay. Can you hear me now? Kazi Saad? Okay. So I said that we don't have any quizzes this time. That's one thing. Final date, I think centrally the authority must have assigned a date for the final exam. I am not aware, I'm sure about that, or I need to look it up. And or we can fix any other date according to our convenience. And final assignment, the project is your final assignment. We don't have any other assignment. Is that clear? Okay. So guys, any question from your side?
No, sir.
No, sir.
What is the convenient time for you to have a class, extra class? Usually
Sir,
Wednesday, Thursday, a little bit, I mean, less, I mean, burden, less load. So
yes, sir.
prefer
Sir,
your Wednesday or Thursday.
Thursday,
What,
sir, I think.
what is the
Sir,
convenient time for you?
sir, like at 7 p.m.
Wow. So,
Yes,
during
sir.
the daytime, you don't have any time?
Uh, during the daytime. Then,
Yeah,
sir,
I think we have free time on Tuesday,
Tuesday,
Thursday. Sorry, sir, Thursday.
Thursday,
Thursdays.
sir, after 12 p.m.
After 12 p.m., anytime after 12 p.m. or just 12 p.m.?
Uh, sir, I don't know about others, but I'm free at that time.
Okay. So if others they don't have any problems, maybe you can have around 12 p.m., right?
Yes, sir.
Okay.
Sir, it would be better if we let you know through the classroom, Google Classroom.
Sure, no problem.
Okay, sir.
Uh, I'll be available anytime between 12 and 5, so you can fix it. Any other
Okay.
time within that window time.
So it will be, sir, two consecutive classes, right? Or one?
Maybe one long class, not two will be too much. I think maybe one long class will be good enough. Maybe 2 hours.
Okay, sir.
Okay, guys. So that will be all for today, and we'll see you in our next class. So stay well and stay safe. And Allah Hafiz.
Allah Hafiz.
Thank you, sir. Assalamu
Allah
alaikum.
Hafiz, sir. Assalamu alaikum.
চলে গেছে
Fahim.
রেকর্ড হচ্ছে তো জামুল
Sorry.